Kinese 310, Anatomical Kinesiology. This is Dr. Campbell coming with your next lecture on bones and articulations of joints. But before I get started, I have a special guest here because I can't just teach to an empty room. So I have a special guest here who wants to say hello, and he'll just be quick. But come on in, Santa. Hey everybody, it's Santa Claus. Yeah, I just want to say Christmas is coming up very soon, and so if you need a Christmas gift, why don't you go to Buc-ee's? Yay! We have everything at Buc-ee's. Probably have your textbooks at Buc-ee's too. So I just want to say hello. I'm going to be watching this class today and spend all your money at Buc-ee's. Okay, kids, be good. Thank you, Santa Claus. That was so nice of you to say and promote capitalism, I guess. So, in your textbook, segueing directly into class, bones. So, what are we going to need to know for the test? Eventually, you're going to have to know the major bones that articulate the joints of importance to us, the mostly movable joints, shoulder, hip, knee, that kind of stuff. But we do have other bones that are of importance to us that serve as like foundational support, like in our pelvis, that summate motion, not through two, but through many. I'm going to use an analogy with a slinky later on to explain that. So before we get into joints, we kind of have to have a basis of why do we have different kind of bones in our body. And they are to serve purpose, to serve function. In grad school, we learned about simple machines in engineering, and what was the purpose of the different levers, and that was to serve functions. So sometimes it's literally as easy as understanding what the function is to see what type of bone it is. Okay. So the first one we're going to talk about are flat bones. So remember, these are major classifications of bones. Then we're going to connect the bones into, I look like Anakin Skywalker from Star Wars. There it is. Then we're going to connect the bones to talk about joints or articulations. And then we'll kind of give the different types of classifications of joints. Okay? It's so weird teaching in front of just one person. So you have flat, irregular, short, and long, and then we put sesamoid. Sesamoid is a subclassification of flat, but so many students say it as its own classification that I added it on the main ones just because, that's what a lot of people say. So let's talk about long bones. Long bones facilitate movement. So if you think about, so this is a humerus. This is specifically the left humerus, so it'd be here. But like if you think about somebody swinging on a swing, let's go with the wrist. You could swing, you could swing at the elbow, then you could swing at the shoulder. But when somebody's on a swing, there's a lot of motion there. Okay, facilitation of motion. And the longer the swing, ça c'est something. Thanks, Power Saver. The longer the swing, like the chain or the rope, the more movement you're going to get from the swing, right? So it kind of makes sense that if we want to facilitate motion through rotations, we need long ropes, in this case, long bones, long levers, long rigid links, all that stuff kind of sense, so that we can have significant sweeping rotational motion. Okay. There's other benefits of long bone that we don't necessarily care about, like the marrow and storage of calcium. We'll let the physiologists worry about that. We're just concerned about movement, things that influence our motion. So long bones, great for facilitation of motion. Okay. Short bones. So short bones are kind of like the bones in your wrist, the carpal bones, bones in your feet. Let's see, come see, buddy. The tarsal bones. Let's see, you see those right there, the tarsal bones? And what short bones do really, really well is dissipate force primarily. And they can shift and glide, and summation of motion is almost like a secondary benefit of dissipation of force. So how I want you to think about this is, if you were going to jump off of a one-story building, you'd rather land in sand than on concrete, right? Because when you land on the sand, all those grains of sand are going to shift and move and slide. There's a lot of space. There's not a lot of space that we see, but the sum total, there's a lot of air. It's almost like an airbag, poof, that can slow you down over time, dissipate force. So landing on the sand helps to dissipate the force, slow you down over time, and that takes less force off of your joints and muscles, okay? So the same things happen at our hands and our feet, where we have carpal bones to help dissipate force. Why would we want to dissipate force here? Well, because we push on things to influence their motion a lot, whether that's from our feet pushing on the ground, like to jump or to run or to land, or our hands pushing on things in the weight room, maybe like a heavy bench press, or if you had to push and move something, it's a lot of force being applied. And that force has to travel down the chain. And so by having these kind of short bones that have space in between them, we can help kind of dissipate some of that force before it gets transferred on, okay? Another benefit of short bones is the summation of small little movements. So think about it in terms, if we had dominoes and we lined the dominoes up and we wanted to curve something, right? We can take the domino and move a little bit, then a little bit, then a little bit, then a little bit, then a little bit. Very similar to how a slinky works. A little bit here, a little bit there, a little bit there on each rung. The next thing you know, you made a whole 180 turn because of all of those little bits, okay? So short bones. Flat bones, protection, 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 protection. So the flat bones that are in the skull, protection. Your scapula is flat because protection of the back, because we can't see our back. Also, flat bones serve purpose for having a good surface area. Because they're flat, they have great surface area for muscles to originate and attach to. That's why you have so many muscles on your scapula. The ribs are classified as flat. You don't really think of it, because they look long individually, but the rib cage, let's see if I could borrow this guy. See? He's sleeping. The rib cage is kind of like a shield, if you think about it. Think about in the medieval times, where knights kind of had shields for protection, right? It's like a big shield that's protecting the organs and your heart on the inside. Now, it's serrated because it has to expand and contract to breathe. And if this was one rigid bone and you had that kind of tension of expansion contraction, you'd have stress fractures. And so you have cartilage here that kind of gives it, allows these ribs to kind of move independently of each other. But the sum total of these ribs is for protection. You need to protect those organs, okay? So flat bones, great, great, great at protection. Then you have the weirdos. You have the irregular bones. So if I was a bone in the body, I'd be irregular, okay? Because I'm a little different. Irregular bones serve very, very niche purposes. Off the top of my head, like the ossicles in the ear, the hammer incus and stapes, right? Very, very specific functions to transfer vibrations into through the tympanic membrane into our vestibulocochlear nerve and interpreted into the brain. Like, those are very, very niche instruments. The vertebrae are very irregular. Boy, they have to serve a lot of purpose. They have to dissipate force. They have to move, but not move too much. They have to create, when you stack those blocks, they have to create foramen, which are holes that your nerves and vessels can run through. Very, very niche things, okay? So that are irregular. And then the sesamoid up here is a subclassification of flat. So we have subclassifications of things, not a big deal, but its main purpose is a protection. So you think about the most famous sesamoid in the body, the patella, okay? So the patella, and maybe you've been introduced to the patella as like for leverage, right? Increase angle of pull, the quadricep. Not saying that's not true, but you know what else the patella does? It serves as a shield for when you fall and you land on your knee. That patella can protect and absorb some of that force so that it doesn't travel any further up the chain, okay? So it's kind of a flat bone that also serves as a leverage increaser. I love making up words. So those are our main classification of bones. Bones come together to form joints or articulations. So flat bones, when they articulate with other flat bones, it's a joint. They don't move about each other. Well, that's not true. Flat bones can move about other bones, but in the case of the first classification of joint, synarthrotic joints, these are non-movable articulations from the coming together of bones. Most of the time it's flat, but they don't have to be, okay? An example, let me scroll down a little bit. Example, these sutures in your skull. So if my buddy had his head on him, I could show you, but I think you know what I'm talking about. And if you don't, just Google a skull. You'll see all these like borders. So like think about how states have borders. Like if you looked at a map and you would notice like Louisiana borders Texas, and there's like a windy kind of, that's river, but it borders two fixed states. So a synarthrotic, non-movable joint or articulation is a coming together of two immovable bones about each other because they've been fused. Well, why would we fuse them? Why wouldn't we just make one big bone? It's a good question. That's what I asked when I was in your position. And the answer is development. You know, when we're babies in our mother's womb, we're a lot smaller than we are now. And we have to allow for these flat bones to grow independently. So if they were one basketball-shaped bone, they couldn't grow circumferentially because they would keep each other locked. So by being unfused, so that's what growth plates are, they're allowed to kind of expand together and grow together, and then once you stop growing, they seal up. Your growth plates seal up, okay? So that's kind of how that works. Some of the flat bones, some of the synarthrotic joints that are going to be important to us are in our pelvis, where we're going to have the ilium, the ischium in the back, and the pubic bone in the front. So those are three separate bones that, just like in the skull, are allowed to grow and expand and then fuse up, okay? So and the three bones are actually fused together in the socket, the acetabulum of the hip. So one of the trick questions I always ask is, how many bones articulate the hip joint? The answer is 4. You have the ilium, ischium, and pubis, where they fuse together to form the hip socket or the acetabular, and then the ball of the femur. Okay? So that's synarthrotic or synarthrodial joints. Amphiarthrotic joints are slightly movable. And we categorize a lot of things in threes. So what I'll do is, before I talk about amphiarthrotic in more detail, give you the third one, the diarthrotic joints. Those are the most movable: elbow, shoulder, hip, knee, the ones that allow the most movement. So you have a joint articulation that moves none, then you have joints that move the most, so you have something in the middle. That's really what it amounts to. So amphiarthritic. Think of an amphibian who can kind of do both, right? Like frogs can live in the water and on land. So amphiarthrotics are more stable than the ones that move the most, but they move more than the ones that don't move at all. So I think that's the easiest way to see it, that they have more movement than none, but they have significantly less movement than most. And we're going to see, let me see if I give you any examples. Yeah, metacarpals, pubic symphysis. So a couple examples is when you grab things, your hand wants to contour itself around whatever you're grabbing, and so the metacarpals in your hand kind of independently being able to move, not too much, but a little bit, allows your hand to kind of contour around something, if that kind of makes sense. A little bit of motion. And usually the sum total of the little bits is what we're after. So in other words, a little bit of motion here and a little bit of motion there and a little bit of motion here, a little bit of motion there can allow the sum total of kind of wrapping our hands around things we're trying to grip. The power of little bits, a little bit of motion, just like we did with the short bones. A little bit here, a little bit there, a little bit there. A real world analogy is you're saving your money, you're saving your pocket change, maybe, to go out to eat somewhere or get you something. I quote Christmas Vacation all the time, and since I brought out Santa Claus, National Lampoon's Christmas Vacation. Go get you something real nice, or Cousin Eddie. So little bits of motion can be summated to create significant motion, just like little bits of pocket change over time can summate to be significant where you could buy something. One day of pocket change may not be able to buy me a Coke or whatever, but 30 days of pocket change, significant. So again, like with the slinky, one little change of a rung, not significant, but the sum total of all of them can be of significance. So amphiarthrotic joints are just looking at not the sum total, it's the 1 day of pocket change. It's just looking at how one bone or two bones articulate about each other very insignificantly, more than none, but a lot less than most. And then that's going to segue into a diarthritic gliding joint that does look at the sum total of all. So in other words, if I do this with the slinky, the diarthritic gliding is the gliding of all the pieces that got me to 180. But the amphiarthritic, slightly movable, is just the articulation between any two of these rungs and how that was very, very insignificant. The sum total of a lot of insignificance can be significant. I don't know if that's helpful or confusing. Another example is the pubic symphysis in our pelvis, how our pelvis can slightly rotate there. Let's get to the diarthritic, because those are the ones that we're going to be studying the most in these classes, okay? We labeled them based off of least to most movement, and you have gliding, pivot, hinge, ball and socket. Glidings are once again, the sum total of a bunch of little bits. The slinky, the reason I have the slinky here is because that's kind of how your cervical vertebra works. Right? The sum total of a bunch of little bits. Okay, so it's the sum total. If think of it like this: when people have their fusions, or like they have back surgery and they fuse some of the vertebra, what do they lose? Motion. They lose motion, so they can't contribute with those little bits anymore. Okay. That segues pretty well to, I'm going to go to pivot next, or trochoid or pivot. That is specifically a uniaxial joint, a joint that can move in one plane, one of its planes at a time, one of its axes at a time, and specifically for spin rotation in its transverse plane. The reason I'm going to go there next is because atlas axis, if you remember from biology, that is a pivot or trochoid joint. That is a articulation of the atlas and the axis. Remember, atlas holds the base of the skull and it rotates about the axis. So the other day, I was talking to a friend of Ms. Carol Trosclair, and he had neck surgery. And he said, you know, they fused this. And I said, how's your motion? And he said, my motion's fine. And he rotated, but he only did the range of motion allowed by atlas axis. So in other words, he couldn't contribute any more from C 3, 4, 5, 6, 7 about T1. That's pretty cool. Okay. Another uniaxial pivot joint is our radial ulna joint. This is not happening at the wrist, it's actually happening at the forearm. If I just move my wrist, you don't see my forearm sleeve move. But when I move my radial ulna joint, that's literally the radius rotating and wrapping or unwrapping itself about the ulna. So that's an example of a uniaxial. You can see my middle finger serving as a polar axis right here. If my hand was down, it would still serve as a polar axis. But it's uniaxial, meaning that it can rotate about one axis, one of its axes. Come on, buddy. I'm trying my best here. I know you want to conserve power. I don't know why I started talking like I was working at Buc-ee's. Welcome to Buc-ee's. So, where was I before the computer distracted me? Uniaxial. When you hear things that are non-axial, it means they don't rotate. Well, two ways to look at it. They don't rotate about one true fixed point. Or another way to look at it is, for something to have rotation, every point of the segment has to move. So what I mean by that is I have my Ken doll. I don't know if this is Ken, but I needed something to represent some motions and some stuff. And so Ken doll here, and if we rotate the shoulder, let's say, so humerus about the scapula, every point of that shoulder moved. So if Ken represents a segment, rigid link, it could be a cup, it could be my phone. For this to rotate about an axis, every part of this segment has to move relative to a fixed point. That's how rotation is defined. So if you think about it, if you had a tree and the wind was blowing, come on, cold front, like Bob Barker calling down a cold front, come on down. If you have a tree swaying, it's not rotating. It's bending, or we call it curvilinear. But think about it. It's not rotating because the base of the tree, which is part of the tree, isn't moving. It isn't going anywhere. So that's why, like, if someone has a fracture on a bone and the bone bends, we don't say it rotated unless it then you had motion about an axis, and that's a bad day. So bending isn't rotation, okay? So that's why gliding joints, zero axes, because it's really bending. And when we say up to three planes, that is, it can kind of bend in three planes. You can bend sagittally, you can bend frontally, and you can twist transversely. The twisting, notice, is a little different. That's why we're going to have words like rotation. When it's transverse plane spin, it's pure spin. But all of those shifts aren't in one place. So like if we took this and I twisted it, all of those little motions aren't in one place like when I do this. I'm trying to simplify things. So like when I do this, that's all in one place. But when I take a Pringles can and do this, how's a bad analogy? When I take vertebra and do this with it, all of that spin and twist, when I do this, all of the C7 through T2 isn't in one spot like C1 and 2 is in one spot, okay? Atlas rotating about axis. But all the rest of them aren't in one spot. It's this to that, that to this to this to this. Okay, I hope that kind of makes sense. Hinge. Now we get to the butter and the bread. Doors have hinges. Our computers have hinges. Our doors have hinges, like if we're getting out of our car. And some of our articulations are hinged. So our elbow is a classic example of a hinge, a uniaxial joint that moves in one of its planes at a time, about one of its axes at a time. And typically these hinge joints get us into and out of fetal. So our fingers are hinged, not our thumb, that's a special joint that I'm going to talk about called a saddle joint, and not our knuckles, because our knuckles can get us in and out of fetal, but our knuckles can also fan out, okay? But all of our little interphalangeals are hinges. My thumb interphalangeal is a hinge, my elbow is a hinge, my ankle is a hinge. The ankle, the plantar flexion, dorsiflexion, not underneath it. We're going to talk about that when we talk about the subtalar and transverse dorsal joints. So hinges, uniaxial, can move in one plane at a time, about one axis at a time. Just got cultured axis, chicken au gratin, as my brother used to say. I don't know why he said that. I guess it sounded smart. So we've talked about pivots, uniaxials. We've talked about hinges, uniaxials. Ball and sockets are the most movable. That's your shoulder, your hip. It's a triaxial, so the shoulder can go sagittal, frontal, or transverse. It allows the most motion. Some people use fancy terms like degrees of freedom. That just means it can move in any of those three planes and any combination of those three in normal allowable motion. So imagine having an Etch-a-Sketch, little thing that we used to play with as a kid. Used to play with. And it has two knobs because it's in two dimensions. So I have like an up, down knob and a left, right knob. Now imagine if that Etch-a-Sketch had a third dimension, like it was like a shadow box Etch-a-Sketch, and it had a third knob where you can go up, down, left, right, and, well, when I say up, down, so if it's like, if you're looking at the Etch-a-Sketch, it could go up, down, left, right, but it could actually come forward and back. That's a linear analogy. Rotational world, I can rotate about the side to side. I can rotate about the up, down, and I can rotate about the front, back. Okay, so that's why the shoulder and the hip are the most movable, because they can play in all three dimensions. We do have biaxial joints that I'm going to get to, and I need to add it to this, okay? And it's called ellipsoids. Make sure it didn't get shifted. I don't think it did. So I think the intent is to kind of start basic and not overwhelm you. But when we get to the wrist, I'm going to teach you that it's a biaxial, like a bicycle, unicycle, bicycle, tricycle, uniaxial, one axis, one plane, biaxial, two axes, two planes, triaxial, three axes, three planes. Okay? So let's check for understanding here. Objects that can move or rotate in one plane about one axis can rotate two different ways, can spin two different ways. That's what clockwise and counterclockwise mean. So I have a fancy example. So you and I are both seeing frontal, true? So this clock can rotate clockwise or counterclockwise in that frontal plane. One plane of motion about one axis. See what I'm trying to point to? Thought I had a pin. You see it, little black dot is axis, but two different motions, two different ways we can rotate in that one plane about that one axis. Cool? So if you had something that could also spin in the sagittal plane, you'd have the same thing. You'd have clockwise and counterclockwise rotation. And in the transverse plane, you'd have clockwise and counterclockwise rotation. And all we have to do is, instead of saying clockwise, counterclockwise in the sagittal, clockwise, counterclockwise in the frontal, clockwise, because that's kind of that reference would be tough, because that would depend on kind of how you're seeing it, right? So that's why we have terms like flexion, extension, ab and adduction, internal, external rotation. Notice that those joint motions have an antagonist. They have a counter. They have a mirror. It's a duality. If I have flexion type movements, I have to have something in the opposite direction of spin. Flexion, extension. If I have abduction type movements, I need to have something in the opposite direction of spin. Adduction, clockwise, counterclockwise. Okay. So a uniaxial, let's see if I could bring this home. You can do it, Brian. You're doing a great job. Shop at Buc-ee's. So let's say I have a uniaxial hinge joint. Without telling you the joint, you should be able to logically deduce it can rotate in one of its planes at a time, about one axis at a time, and I'm going to have two motions accountable for. Make sense? So see if I could think of an analogy. My elbow, uniaxial, it could rotate in one of its planes at a time. That's its sagittal plane. So in other words, even if I change it, it doesn't change its view of things. So here's sagittal for the elbow. Here's also sagittal for my right elbow. Uniaxial, one plane, one axis, two motions. Biaxial, two planes, two axes, four motions. Make sense? So I told you the wrist is biaxial. So that means it can move about its anterior posterior axis, frontal plane stuff, clockwise, counterclockwise, or counterclockwise, clockwise, doesn't really matter. Radial deviation, ulnar deviation, we gotta have names for it. And it could also move about its bilateral flexion, extension in the fetal, out of fetal. So the shoulder in anatomical position is triaxial, 3 planes, 3 axes, pause it in if you have to, 6 motions. Flexion, extension in the sagittal, ab and adduction in the frontal, internal, external rotation in its transverse. Okay? So I hope this helps clarify when we start to get into specific joints of the body in more detail, the ankle, the subtalar, the knee, the hip. I'm going to refer to, hey, the ankle is a uniaxial hinge. The subtalar and transverse tarsal joints are gliding joints, summative gliding arthrodial, the sum total of a bunch of amphiarthrodials that come together, all the pocket change, and we can get significant motion of our subtalar joint. The knee is going to be a modified hinge. I'm going to explain that in class. Don't need to know that for your first test. Hip is going to be a triaxial ball and socket, like that kind of stuff. So I hope that helps. I'm going to put I'm going to post a kind of summary, let's see how they worded it, checking for understanding post Friday or Saturday, just for you to kind of go over. Almost think of it as kind of a little, say a quiz, but just checking to make sure we're on the same page going into exam week, which is soon. I don't want to say it in the video in case I reuse the video. So it's coming soon. So hope to see you guys in class. Hope this helped. Feel free to ask any questions or follow-up stuff and give me some feedback. And everybody stay safe. See you.